Welcome to the Chemistry 209 Masterclass series. This series of lectures is intended to highlight the key concepts of introductory spectroscopy and structure. This lecture, Masterclass 8, discusses our description of vibrating molecules. We are now becoming familiar with the fact that molecular bonding is an electronic property. Stable molecules may be viewed as minima on electronic potential energy surfaces. Within these electronic minima, stationary states associated with vibrational wave functions give rise to vibrational energy levels, and each vibrational energy level is associated with a ladder of rotational energy levels. Vibrational transitions usually occur in the infrared region of the electromagnetic spectrum, and for this reason, vibrational spectroscopy is often called infrared spectroscopy. Vibrational energy level structure is determined by the force constants of vibrational motions, bond stretches, and angle bends and torsions. Thus, IR spectroscopy facilitates determination of bond strengths and allows us to identify functional groups in molecules. If, during the course of vibration, there is a change in the molecular dipole moment, an oscillating electric field is produced which has the same frequency as the vibrational frequency of the molecule. The electric field of light can interact with the molecule via its oscillating dipole field to induce vibrational transitions. This classical view of our spectroscopic interaction provides an intuitive picture for vibrational transitions. Of course, quantum mechanically, we know that light energy can be emitted or absorbed if the photon energy matches the energy gap between two energy levels, and if the transition dipole moment is non-zero. It is apparent that diatomic molecules must be polar to be infrared active. Polyatomic molecules can, however, be nonpolar and still exhibit an infrared spectrum. This is exemplified by carbon dioxide. Here, the degenerate bending and asymmetric stretching motions distort the molecular geometry so as to induce a molecular dipole during the vibration. As a result, CO2 can absorb infrared light at the degenerate bend and asymmetric stretch vibrational frequencies. We begin our development of vibrational energy level structure with the classical harmonic oscillator model. Here we are viewing molecular bonds as if springs are connecting the atoms. We can describe the forces acting on the atoms in terms of spring force constants and atomic displacements from their equilibrium positions. Thus we find that the potential energy is described with a parabolic curve for a one-dimensional vibrational motion. Recall that the classical vibrational frequency for a harmonic oscillator is nu equals 1 divided by 2 pi times the square root of the force constant divided by the reduced mass for our system. Molecular systems require a quantum mechanical description. If we substitute the harmonic oscillator potential energy expression into the Schrödinger equation, we find that vibrational energies are equal to the product of Planck's constant, the classical vibrational frequency, and an index v plus a half. Here, v is the vibrational quantum number. Usually, vibrational energies are labeled as g of v, and they are reported in reciprocal centimeters. We also collect all constants into a single term, omega e, which is known as the harmonic vibrational constant. Thus we see that the harmonic oscillator model predicts equally spaced, non-degenerate vibrational energy levels, and that the lowest energy level, where v equals 0, has an energy of 1/2 omega e. This gap between the lowest quantum state and the minimum of the potential energy well is known as zero-point energy. It arises due to the uncertainty in position and momentum as described by the Heisenberg uncertainty principle. The harmonic oscillator model predicts that all vibrational transitions will occur at exactly the same energy. Fortunately, vibrational spectra are much more interesting than harmonic oscillator predictions. If we expand the dipole moment operator as a Taylor series, we find that overtone transitions become weakly allowed. This means that the vibrational quantum number can change by more than plus or minus 1 during a vibrational transition. Furthermore, the harmonic oscillator is actually a poor model for the electronic potential energy since it implies that bonds can never break. A more realistic model would introduce anharmonicity, or deviation from the harmonic model, by incorporating a bond dissociation asymptote. Finally, there is no angular momentum associated with radial vibrational motion. Since angular momentum must be conserved, a simultaneous change in rotational quantum number must occur during a vibrational transition. In other words, vibrational spectra may be better thought of as rho vibrational spectra. A commonly used anharmonic potential model is the Morse potential. This analytical function incorporates a long-range potential energy asymptote to account for bond dissociation. Quantum mechanical treatment using the Morse potential results in a description of vibrational energies that resembles the harmonic oscillator result, but corrected with an anharmonicity constant, which results in a decreased level spacing with increasing vibrational quantum number. When discussing vibrational transitions, we use a special labeling scheme. The transition between V equals 0 and V equals 1 is known as the fundamental band, and it is usually the dominant feature in the vibrational spectrum. Excitations from V equals 0 to V equals 2, 3, 4, etc. are known as the first, second, third, etc. overtone bands. Any vibrational transitions not involving V equals 0 are collectively known as hot bands, since molecular samples usually have to be at a relatively high temperature for these transitions to be observed. Note that vibrational transitions are typically referred to as bands because they occur over a range of frequencies owing to rotational fine structure. We can also now define a zero-point energy, which is the vibrational energy of the ground state, and dissociation energies dE, which gives the potential energy well depth, or d sub V, which gives the dissociation energy from vibrational level V. To conserve angular momentum during a vibrational transition, molecules undergo simultaneous rotational transitions. Thus, in our development of molecular energy structure, we must now consider combined rotation-vibration terms. The rho vibrational energy of a molecule is merely the sum of the vibrational energy, g of V, and the rotational energy, f of j, which, for an anharmonic non-rigid rotor, is given here. To calculate rho vibrational transitions, we must take the energy difference between the upper rho vibrational level and the lower. These transitions are subject to the rotational and vibrational selection rules that we've already learned. For example, we now know that there is a rotational selection rule of delta J equals plus or minus 1. If the upper level J value is 1 greater than the lower level J value, the transition is referred to as an R-line. If, on the other hand, the upper J value is 1 less than the lower J value, the transition is a P-line. Owing to the fact that delta J is plus 1 for R-lines, these transitions result in a net gain in rotational energy. Consequently, R-lines form a series to high wave number of the vibrational band origin. The delta J of minus 1 P-lines, on the other hand, form a series to the low wave number of the band origin. These series of rho vibrational transitions are known as branches. Q-branch lines corresponding to delta J equals 0 transitions are also possible in vibrational spectra, but require simultaneous change in electronic or vibrational angular momentum. As we will see in Master Class 11, Q-type transitions are much more common in electronic spectra. As was the case with pure rotational spectra, isotope effects are also important in rho vibrational spectra. Here we see that the reduced mass of various isotopes affects both the vibrational and rotational structure. A classic example of this is the rho vibrational spectrum of hydrogen chloride. Owing to the fact that the deuterated isotopologues have reduced masses that are nearly twice those of the hydrogen-bearing isotopic species, the DCl isotopologues have lower vibrational frequencies and smaller rotational constants. Consequently, the DCl band structure is much more compressed than that of the HCl isotopologues, and the fundamental band origins are shifted approximately 800 reciprocal centimeters to lower wave number. Note the expansion of the P branches and bunching of the R branches with increasing J. This occurs because the excited V equals 1 level rotational constant is smaller than the V equals 0 rotational constant. This difference in excited and ground state rotational constants arises due to anharmonicity, which results in increasing average bond length as a function of vibrational quantum number. The small value of B' compared to B" means that the excited state rotational energy level structure is more compressed than that of the ground state. Owing to the quadratic J dependence, events, the J double prime to J double prime plus 1 energy gap eventually overtakes the J prime plus 1 to J prime plus 2 gap, thus causing the R branch to reverse direction along the wave number axis. The point at which a rotational branch turns around is known as a bandhead. Since the difference in rotational constants is usually relatively small, rho vibrational bandheads typically occur at very high J values. Consequently, bandheads are usually only observed in vibrational spectra of very hot molecules. As we will see, low J bandheads are common in electronic spectra and can be observed in either the R or P branches. When analyzing rho vibrational spectra, it is often beneficial to use the combination difference method to isolate the rotational energy level structure in one of the vibrational levels. By taking the difference between the R and P lines that share a common excited rho vibrational state, we calculate a rotational energy level gap in the lower vibrational level. Likewise, taking the difference between R and P lines that share a common lower state gives a rotational energy level gap in the upper vibrational level. The combination difference method is useful for determining molecular parameters and is also often used to determine rotational assignments for complex or unassigned band systems. See you next time.